Let's see. Naught. Mod 3. That's fine. Now 1 mod 3 is 1 congruent to 0 mod 3? No. Is 2 congruent to 0 mod 3? No. Is 3 congruent to 0 mod 3? Yes. Okay. Now 4, 5, no, 6, yes. So what's going to happen if we have this? So if we have a 0 here and a 3. What's that? I mean, sort of like this. What's this going to be equal to? Well, so your mod is 3, and it's the set of all numbers congruent to 0, right? To this. Right? So that is that. And what is that? Well, it's just 3z. Make sense? Is that sort of plausible? Okay, now similar, racing ahead a little bit. If we now put 1s here, if we have 1s here, so 0 is not congruent to 1, mod 3. 1 is congruent to 1, mod 3. So now if we keep going down similar to this, you'll get something like this. So the set of all integers that are congruent to 1 mod 3 will be 3z plus 1. Okay, so in other words, 1, 4, 7, 10, 13, 16 and so on. Okay, and now because we've got mod 3, we can have a 2 here. We could have 2 here. So this will be 3z plus 2. Okay. All right. Now, in the case of mod 2, we had 2 of these sets. And in case of mod 3, we have 3 of these sets. Now, I'll remind you again, what is this? What is this set, or this set, or this set? What are they? This is the set of all integers congruent to 0 mod 3. This is the set of all integers congruent to 1 mod 3. And this is the set of all integers congruent to 2 mod 3. Okay? These sets, where this number here is sort of the residue, instead of calling them residue sets, they're usually just called residue classes. Right? So we have, that's a residue class, that's a residue class, that's a residue class. So in this context, a set and a class, same thing. Okay. Now let's generalize this and go to mod n. So the residue classes would then be the following. Okay. Does this seem plausible? Dot, 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 right down to n minus 1. Okay. So if your mod is n, you will have n distinct residue classes. And if you union, like union all of these classes, you will get z, right? You get all the integers. So this is the set, or the residue class. It's the set of all integers that are congruent to 0 mod n. So this set consists of, if you think about it, 0 plus or minus n, plus or minus 2n, plus or minus 3n, and so on. This one would be the set of 1, and then 1 plus or minus n, and then 1 plus or minus 2n, and so on. Okay, so now, and if you union, you bring them, you add the two sets or n sets. So if you union like this, all these sets, you will get the full set of integers, right? So you can split up the set of integers, z, into mutually exclusive residue classes. So this one is just nz, that one becomes nz plus 1, and so on. And this last one would be nz plus n minus 1. So these classes, these sets, are in a sense subsets of z, of the set of integers. Okay? Now interestingly, and I'll give you I'll give you one more theorem, so watching the time as well. Now these residue classes, they behave somewhat like integers. So you can actually do an arithmetic on these classes. So talk about here an arithmetic of residue classes. So if I put an n here, okay. So now if your modulus is n, you will have n of these residue classes, and you can add them in the following sense. So let me try to prove this case. So residue class A mod n plus residue class B mod n is equal to the residue class of A plus B mod n. So it's sort of like arithmetic. But remember, these are sets, right? They're a residue class or a set. Class, set, same thing in this context. So how to prove that? Let me try to prove that. So this would be theorem 8. Okay, so let's so theorem 8. I'll stop after that. So theorem 8 says that if A is congruent to B mod n, and C is congruent to D mod n, then well, two things. So two things, A and B. So A plus C, so you add these two, is congruent to B plus D mod n. So that's like addition. It's an addition form, and there's something similar for the product. And if you multiply these two together, then AC is congruent to BD, so the product mod n. Alright, so let's prove those fairly quickly. Alright, okay, so A and B are congruent, okay? So that means you can write A minus B in the form of in what? In H. Okay. And C and D are congruent, so you can write that in a similar form. And what puts K. Okay. Now, if they're congruent, remember this N divides into the difference, A minus B. That's the definition of two conjugate numbers. Okay, so you've got this form. Right. Well, let's add A and C. If we add A and C, well, I mean this take the B over, so you got B plus NH, and C here will be take the D over, so D plus NK. Right. So now add A and C. So you'll get A plus C equals this plus this. And that will be B plus D, you add these two, plus N into H plus K. Okay, follow that? So therefore, now take the B plus D over, so you'll get A plus C minus B plus D equals N into H plus K. Right? So that means that that number and that number, that integer and that integer, they are conjugate. Why? Because the difference you can divide N into. N divides into the difference. Okay? So you've now proven that A plus C is conjugate to B plus D. Okay? Mod N. Now, I won't do this case, it's pretty easy. I mean, it's somewhat similar to this. So I'll leave that as a homework exercise. And I'll stop here for the theory, and then quickly we'll do some exercises. In the textbook there are very few exercises for this chapter, and they're fairly easy once you've understood the theory. So that will only take a few minutes. So I'll stop here, and the next portion will be problem solving.